Welcome, everybody. Tonight, we're going to be working on the first of two units that cover supervised learning. This is part one. We're going into unit five, so the fifth week of instruction here for our course. We are going to start by kind of relearning some of the concepts that go with machine learning. So there's two reasons for this, by the way. When we were in the intro to AI course, we talked about machine learning as a subset of artificial intelligence and its main precepts. And we've talked about them more in this course, but we're going to reiterate exactly what certain aspects are for clarity. Plus, we also have the possibility that there are people in this class section that did not yet take the intro to AI course because it's not a prereq for this one. Only Python is. So it's kind of to reinforce those concepts. But remember, as I've told you, that the more you kind of repeat information, the more you tend to remember it and what it means. And so if it's a little redundant, at least to start with here, think of it as, solidifying it in your subconscious or something, so that you really know it. We're going to cover all of these topics here tonight. But let's take a look at some of the fundamentals to start with, right? So we're going to go back and learn what these machine learning algorithms even are, what the categories are. And a lot of this stuff should sound familiar and refresh what we learned in the previous course a little bit. And for those of you where it's brand new, you'll want to pay extra close attention, I guess, right? To get the concepts so that they sink in adequately. All right. As the slide says, right? All right. So they're going to throw a scenario at us like this. So they say Sam's a student and he either likes his classes or hates his classes, right? And it depends on what level of learning is involved. Is there math in the class? And how the class is delivered, right? So for example, like we're on Zoom. Maybe you like that, maybe you hate that. I don't know, whatever. Some people like in-person classes better. Some people absolutely hate that. Some people like to listen to people lecture. I'm not really a huge fan of that. Unfortunately, this class has a lot of that, right? But we have to get the concepts across, right? And then there's other classes where you're much more hands-on. And this is kind of the general scenario here. So basically, if you look at this little chart here, the y-axis ranks the mode of delivery. So in other words, if the data is at the bottom end, the delivery of the class is more lecture. It's just, here's the theory behind it, right? And if it's on the top end, it's more activity based. And it seems like he prefers more activity based learning than theoretical. Also, the levels of learning, he tends to not like the easy classes. I know this stuff already. Get me to the good stuff, the stuff I want to know, right? But there's always a process to get there. And then basically what he did is that we're grouping the classes. So there's a data point for mode of delivery and a data point for levels of learning, and it fits on the matrix like this. And the ones he likes are the ones that are grouped together in green, and the ones he dislikes are the ones grouped together in red. And you can see two very clearly formed groups on the screen, right? They're clustered together, right? So he likes more activities, he dislikes theory, and he likes stuff that's more challenging. Okay. And when we group things, we're classifying them into like and dislike, right? And we can kind of see it. Well, we can see it with the color, but we can see it with the groupings as well. But now, that's the stuff that we know the data. So we like say, hey, how do you like your math class? Or how do you like your English class? Right. And he would just tell you. But what if we have new classes that he hasn't taken before? And we can look at maybe the syllabus or something and figure out, is this really a lot of lecture or is this real activity based? Right. So we have two new data points, the dark blue and the yellow. Right. We're throwing that in. And those are not predetermined as to whether he likes or dislikes. They just land on the graph. Now you notice the A one, the blue one, fits clearly in the circle with the green ones. Okay, it's got to be alike, right? I mean, that's what we'll guess. But the B is not in one group or the other. So how do we know if he likes it or dislikes it? It's kind of in the middle, right? It is. So we can't really just say where it's going to fit. So how do we figure out how it's going to fit? That's really kind of where we go. So we use a couple of techniques here, and we use the nearest neighbor technique, right? And we'll learn later this is a KNN and there's a K number to indicate all this. But anyhow, that we take a grouping of stuff in the middle. So what are the points that are nearest to it? And notice that we get two that are green and one that's red in the circle that's nearest. So he still might dislike it, but right now I'm getting two greens and a red. Greens beat red. I think we're going to go with he's probably going to like it, right? And these are how some of these predictive algorithms work. So when we learn about KNN, that's how that works. And what we do, and what's interesting about this algorithm is when we draw the circle, what would happen if I would have had two reds and two greens? Right. Never choose an even number of nearest neighbors, because that way you have a deciding vote for sure. Right. That's part of the algorithm as well. And we'll learn about that. All right. So what is then technically a machine learning algorithm? And it says it's a subcategory of artificial intelligence, and it effectively automates the process of analytical model binding and allows machines to adapt to new scenarios independently. All right, so that's very, very wordy, but keep reading the bullets here. So the machine learning learns from the data, builds a prediction model, and then when a new data point comes along, it can easily predict what category it falls into. So it can, based on what's happened before, it can figure out what's going to happen with the new data points. And so the thing that helps it, you feed it a lot of data. The more data you feed it, the more accurate it becomes, right? Based on experience. Yes. All right. So now we'll look at the three broad categories here, and we'll start by defining AI models. And basically, they're programs that have been developed and trained on a particular set of data, right? We did a little bit of this in the last class. So you get like if you might have a whole bunch of data, but you'd never use all of it to train your model, you use a large portion of it to train your model, and then you use the remainder to test the model to see if the training worked, right? But basically, you develop it and you train it on a set of data, and then we use some sort of AI framework to help us recognize patterns, right? And the frameworks are, of course, depending on the kind of math and scenarios and anything. In machine learning, we have these three basic, categories of machine learning models or algorithms. And we've talked about these in the past. So hopefully this is a little bit of, refresh from the last class. We have what we call supervised learning, right? So in other words, the data that you're working with is already labeled. That's an apple. That's an orange. That's a banana. That's a guava, right? It comes with the information. You know what it is. Then you have the unsupervised, where it's learning based on information that's not labeled. Somebody didn't say it's what it is, right? And then there's the reinforcement learning, which is where you use kind of a reward punishment system, so to speak, right? And if you guys remember the example video we played was like a Pac-Man video, right? Like eventually the AI figured out how to like kind of beat the game and get to the next level, right? But at first it would be like us sitting at an arcade machine dropping dozens of quarters in to figure out the right pathway, right? But those are the three approaches to create, or the three large categories. When we get into the supervised area, we start with a set of data that is pre-labeled. So in other words, We don't have to um, do that task because it's already been done, right? This is one of the ones that's been used the most historically because it's the least complicated and the easiest one to employ. And it replicates human learning. And this is how, right? When you're a kid, right, what do your parents do? How do they teach you how to do stuff or what things are called? You see a dog walk across the street. Yeah, that's a doggy, right? They're labeling it for you. They're giving you the parameter, right? So that's why it's like human learning, right? They're telling you what it is. So the next time you see a dog, it might be a different breed, size, shape, whatever. And you're like, that's a dog too. It's different, but it's definitely a dog. It's not a cat, it's a dog, right? So the goal of the algorithm is to form to learn from correct answers, right? So you learn based upon what you already know is true. And then when you get a new piece of information, very easy to make predictions because of what you already know, right? When we do supervised learning, we basically do it in these two larger categories, regression and classification. Regression, of course, refers to very specific types of mathematical correlations, right? And you know, the linear formulas and all that stuff that we were talking about all fall into that. It can predict a continuous numerical value. So no matter like what piece of data you throw at it, the model will be able to predict pretty closely within a range of variance an accurate answer. Like, so for example, like if I drive 500 miles, I should know how much gas I'm going to burn. Maybe not exactly, right? You might be driving faster or slower or uphill or with more weight or whatever, but you can get it within a very particular range, right? That's going to be very accurate. And the data is continuous. It doesn't matter how many miles I drive. I can probably tell you how much gas it's going to consume, right? Then you have classification, which is the labeling. So like, is that, like the example I have, is that a car or a truck? How do you know the difference? Then you have the unsupervised learning. This is where we use data that's not labeled, right? Um, and we're looking at information that's basically raw, and we're looking for patterns in it. Well, those kind of look the same. Those kind of look the same, but those two groups don't look the same. You know what I mean? It's not labeled, but we're recognizing what matches, right? There's a few different approaches. We've talked about a number of these too, right? Albeit superficially. Clustering, things are together, right? Uh, Density estimation, and then anomaly detection if stuff is like way out in space. And then we did the PCA thing just recently, looking at that aspect, right? So that's an aspect of unsupervised machine learning. What's interesting about this is this requires some labeled data to begin to learn what the unlabeled data is. This is kind of weird, right? So you might have to like do, and when they say input and output pairs, what they're saying is that, well, with it, given this input, what is the output? All right, well, given this input, what's the output? And then you start to see what happens, and then your patterns get established, right? But you do have to have the inputs and the outputs. And it says these algorithms use input data only to do the pattern recognition, right? All right. So we're looking for patterns. We're looking for organization or structure, whatever you want to call it. The other one is the reinforcement learning. And this is basically a trial and error approach. All right. I'll keep sticking my finger in the light socket and see if I get electrocuted. Eventually, I'll probably get smart and stop, right? And put my finger in the peanut butter jar instead, or whatever. Bad joke. But the point is, you try, and if it fails, okay, well, try something else. That didn't work, right? And it's really a punishment reward system that we're using. And of course, they have this little maze game here where like the mouse can go through the maze, and if it hits the lightning bolt, it loses points. But if it hits water or the cheese, it gains points, right? So, and what you're usually trying to do is maximize the positive and minimize the negative when you do reinforcement learning, right? This is also not perfect, but it does work pretty well. So what happens is we create algorithms then that observe what happens and then start to identify what we think is the correct thing, and then and as they say here, minimize risk and maximize reward. We want to increase the positives, minimize the negatives. And notice it says this is an iterative approach. Remember what iterative means, right? That means to reiterate, to do it over and over again. And, you know, the more you do it, the better the training will be, right? So how do you get really good at Pac-Man? By playing it a lot, period, right? Yeah, I was never big on Pac-Man. I was more of a Space Invaders guy back then, or asteroids, I think. All right, so this is kind of an overview then of all that machine learning stuff, right? Machine learning allows computers to learn without being explicitly programmed. There's three different types of learning: supervised, unsupervised, and reinforcement. Those are the broad categories. Supervised learning is a relationship between input and output, and the algorithm's trained with labeled data, and the goal is to make predictions given new data. Unsupervised looks at the relationships between variables that are not necessarily known, and the goal is to gain knowledge and find structure. We're looking for those patterns. And reinforcement is the trial and error thing, maximizing the good, minimizing the negative. All right, so that's kind of the synopsis of machine learning. Yes, we're skipping the discussion. All right, we're going to go back to our friend linear regressions. Isn't this like a fun topic? Right, and we're going to kind of stay mired in the math world kind of for the duration here. So buckle your seatbelts, approach it with an open mind, and don't hate math, and start to understand that you can look at it from a high level, right, and not have to freak out to it. All right, so why is linear regression one of the most important mathematical things that we can learn for this stuff? It is really kind of one of the most fundamental forms of being able to analyze data, real frankly, is why. And this is where a lot of it stems from. We often, when we're looking at information and we, like the little dots for Sam in the classroom and what classes he likes, right? We'll have an X and a Y axis, we'll have points on a graph, and sometimes we'll have very clear demarcations or groupings or a line that the data forms along an equation. And when we can make really good predictions and we know where that prediction line is, then with a very high degree of certainty, given any input value, we can tell you within a range what the output value will be, right? That's what a linear regression can do. You can use it for a lot of different things. It is particularly useful for doing trend analysis. So for example, if, okay, so let's say I go to school for a certain number of years, and then I go out and get a job, and then I look at all the people that went to school and have degrees, and the more school they did, and then I look at the money they make. Generally speaking, people who have more degrees make more money, which is how it is, right? Not always. You can go to a trade school like Gateway, learn how to do I don't know, welding, and go out there and make big money too. And right, you only went to school for 6 months, right? But generally speaking, you see that correlation. So a PhD is probably going to be making more money than somebody with an associate's degree. It seems pretty intuitive, right? There's a direct relationship. If I see that my sales, if I work at a liquor store, if I see my sales for beer increase every time there's a Packer game, that's a direct correlation, right? And that's the kind of thing that we can look at. If the Packers go to the Super Bowl, I can predict that I'm going to sell twice as much beer in Wisconsin, right? than if the Packers don't go to the Super Bowl. I'm sure you can look at data like that. Um, it is definitely the most common statistical analysis that's done and preferred in many different ways. It uses linear equations typically that plot on a two-dimensional graph. We have variables that fit into the category of dependent variables or independent variables, and then the combo of those two. And notice how they label them. The dependent variables are target variables, and then the independent variables are the predictors. And then combine those together, and then we can get a pretty clear picture of where things are going to go based on the data, right? But basically, the prediction is an assumption ultimately, and why we use dependent and independent variables, because the prediction depends on the variable or the input that we're putting in there. All right. So breaking that down even more, independent variables or the predictors are variables whose value does not change by the effect of other variables. Okay, that's an interesting thought here, right? So if I have a variable and I change it and it changes a different one, okay, then it's not an independent one. We're looking at something that does not change when something else is manipulated. It's usually in these equations denoted as an X. The independent variables are usually denoted as X's. When we look at the dependent variables or the target variables, those are variables whose values do change, right? When there's any manipulation of any of the independent variables. So if I change the independent variables, the dependent variables change because they depend on the independent variables for their value, basically. Usually in these equations, we use the letter Y to represent those, right? So here's some of the general forms of the equation. Now, please be mindful of the fact that these indicate a general form. And the general form is basically our dependent variable, right? The independent variable, the constant, and M, which is the slope of the line. We also call this the coefficient, right? This is a multiplication sign, by the way. And it could be expressed as just Y equals MX plus C, right? But they're trying to show the multiplication and the addition clearly. And that's a simple linear equation with an X and a Y. It'll plot a line on a two-dimensional graph, and you'll have scatter plot points. If you have multiple independent variables, and this happens as well, right? So we still have coefficients. We have the multipliers, right? The M's or the slopes. Each coefficient multiplies with one of the independent variables, but you can have multiple independent variables affecting the outcome of an equation. So each one of these groupings here is really, so this is like one expression. This is like, MX or M times X, really is what that's saying. This is a multiplication symbol here, this one. The interesting aspect of this, right, is that you can take it to a multiple linear regression, and then you can start to throw in polynomials as well, which means numbers added to powers. It's still a linear regression, though, because the core of it is still this part, which is linear. So even though there's multiple expressions here, it'll still plot on a linear graph, right? So this is a polynomial or multiples, with exponents and stuff. All right. Some ways we use linear regression. These are real common examples. We can use it to determine like the GDP of a country, like how much it's going to grow. You get these kind of predictions. Economists predict that the economy will grow, that kind of thing, right? By a certain percentage. How do they know? They must be looking at some data, right? And doing an analysis, and it looks good, so it's going to grow, or it looks bad and it's going to shrink, right? Product price, we can use that to predict what something would cost in the future. Like I could look at like what a can of Coca-Cola cost back in the 70s compared to what it costs now, and then I can predict 20 years into the future, what it might cost then, that type of thing. Or how about estimating the number of houses a builder would sell and at what price in the coming months? Like how much is the market going to change? Or to predict the number of runs a player would score in a game, like if they're playing baseball. What are we basing on? What they did before, right? And baseball is a game all about statistics, right? It's more about statistics than the gameplay, I think. So it says here, what is a linear regression algorithm, right? And basically, take a look at these bullets here because these are really important to this conceptually. It says the variables should be measured at a continuous level. So what they're using as examples are like time or sales or weight or test scores, and they are numeric, right? And they're continuous. And what they mean by continuous is you got a score and there is data for it. Like for example, if you take a test and I score you, you got whatever score you earned. But if you decide not to take the test, well, you got a score also. It's called a zero, right? But that's still a score, and that's data, and it's continuous data. And it could be anywhere. The data could fall anywhere. It could be on certain increments, or it could be anywhere in between. That's also what continuous means. We can take the data points and use a scatter plot, just an XY grid, and plot them with the XYs on the chart. Every time we process a data point, like a different X, for example, it creates a different Y, and those points would be separate points on the graph, right? If there is a regression happening, the data is correlated, you shouldn't have any significant outliers. So for example, if I see that like the more I practice, the more hits I get in baseball, there's a direct correlation. But then everybody has a bad day. Hopefully there's not too many days where they completely blow it, even if they practiced a lot. But that can happen in sports, right? And if there's errors, in other words, if it doesn't fit right on the regression line or where we predict, it's within a reasonable range, and they call it the normal distribution. Most of the answers will be, within like 95% of the results will be within this range, like really close to that point. Right? And we can predict that. That's why linear regression is so helpful, really. All right. So we basically look at two things when we do this that are important. We look at the variable and we say, which are significant predictors of the outcome variable. So in other words, what piece of information can I look at that will tell me what the outcome will be, right? So for example, if I want to know how far I can drive with my car, the biggest factor would be my MPG and how much gas I have in the tank. The types of tires I have, well, that has an effect too, but not as much, right? So I can go farther. I can predict how far I'm going to go because I know my MPG and I know how much gas is in the tank. Knowing what tires I have on the car just might help me go a little farther or a little less far. How significant the regression line is to make predictions with the highest possible accuracy. And this is something we can test for, by the way. We go back to this equation, if you guys remember this. So we have y is the dependent variable. This is the general form of the equation, by the way. We have the slope of the line, which is m. Then we go to the independent variable. You multiply those two together, and then you add the constant. Now, notice over on the graph here is if you plot, and they're no numbers are being plotted in here, just as the example. If I feed in an x, we'll call it x1. It's the first x I feed in. And when I feed in this x1, it gives me that y1. And notice how it falls right on the line. The constant is the point at which we intercept the y-axis, right? And then we can predict for any level of x, if this is the right slope to the line, for any value of x I put in, I can tell you what the value should be. Doesn't mean it's gonna be, right? But what it should be. And then notice that any of the aspects of this equation, right, without, I'm not doing mathematical proofs here, I'm just stating it, I can solve for any one of these. So for example, if I want to look at the slope of the line, here's the equation for it. How am I doing that? Well, with multiple variables. So I have to have at least two inputs, and then I can start determining the slope of the line. And this is how you do it, right? And what they're doing is they're just doing a difference, doing the division, and that tells you the slope. Rise over run is what we're doing. How far is it rising for how far it's run, right? So when we're doing regression with real life data, though, you often will get a data set that's kind of like this, right? So I want you to take a look at this. We have a X and a Y. We don't know what the data is. We're just given numbers, right? And we'll take 1 for X. So 1's here on the chart. Doesn't start at 0. It starts at 1 for whatever reason. And for when I place 1 in here, the output is 2. So there it is. That the blue dots are the actual data. So this must be observed data. When I input 2 for X, it gives me 4. When I input 3, it gives me 5. When I input 4, it gives me 4. When I input 5, it gives me 5. All right. If I look at the mean of each one of those variable sets, the mean for X is 3, and the mean for Y is 4. And if you were to plot the regression line for this, so if I did a scatter plot, and think back to like using Excel, if I do a scatter plot in Excel and ask it to add a trend line, it would put in something that looks like the yellow line. And really, when I put in a 1, I should really be at like 2.75. And when I put in a 2, I should really be at 3.4. Right? That's where it should be. And what happens is this is the prediction and this is the actual. But the actual's not too far off from the prediction. So if I was to go to point number 6, could I follow this line up and probably say that the output will be 6 or right near that, right? That's going to be pretty close. That's what we're talking about here, right? Okay, so here's where the math starts looking scary, right? The sigma, by the way, in calculus and advanced math stands for sum. It's like saying add it all together. So sigma equals 15 means all of the x's add up to 15. So take a look at what we're doing with the data here. This is pretty interesting. We're taking all of the x's and adding them together, all of the y's and adding them together. Then we're taking all the x's and squaring them and coming up with another sum, all the y's and squaring them. And then we're also doing what they call a sum product, right? Take the x's and the y's, multiply them together and add them together, and you come up with this, right? And then if you look at the formula here, right? So they start with the base formula, they pump in all the actual numbers, right? And this will tell you what the value should be at the end. Notice that these equations here, by the way, are solving for all of the separate pieces. So I can solve for M, and I know this looks scary as heck. Don't worry about it, right? Just plot your memory out, you absorb it in your subconscious, your brain will remember eventually. So we're solving for M, and remember, M is the slope of the line. How steep is the line? A slope of 1 is a 45-degree angle. A slope of 0.6 is a little flatter, right? Then C is the point at which it crosses the y-axis, and that point is 2.2. So think about this. If I know where it crosses the y-axis, and I know the slope of the line, I now know the prediction points for all the stuff that could possibly come, right? And it's correlated. The more X I put in, the bigger the Y is, right? Because the line goes up. It's not a steep line, it's sort of flat. right? So that's kind of the point of it, right? So we're just able to pull out uh, that. All right. So once again, m is the slope, and that is the what we call the y-intercept, if you will. Right. So what's kind of fascinating about this, there's mathematical proof behind all of it, right? So like if you want to really dig into this and understand it, we can take then the what this equation really does is it gives us the predicted value of y in actuality. Because when we actually plotted it, right, I'm going to go back to that, the actual plot points weren't right on the line. But what the equation says is what it should be, right? So this tells me that if I put in an x of 1, it should be 2.8. The 2 should be 3.4. And now instead of using letters, we have actual numbers in here. So the predicted value of these are actually this, right? Whether or not the actual values are. But here's what happens. So you have the predicted value, which are the brown or orange squares, whatever color you want to call that. And then you have the actuals, and then there's a difference between those. And it's measurable and quantifiable. And you can do all sorts of statistics on top of that too, right? So we have the actual data and the predicted data and the difference between the two, right? And they call that residual or errors, whatever, right? And then there's really kind of interesting thing that we can do. We can use what they call the sum of squares, basically, and it leads to this fancy constant number called E. And I'm sure a lot of you don't even know what that is, or maybe you learned about it in math and summarily forgot. But E is a number sort of like pi, right? We have a mathematical representation for it. It's a constant, and it's like an infinitely long decimal number that never repeats. And they call it E, and the general value of it is like, I think 2.1, 2.78 or something like that. I forget. But it's used in these what we call logarithmic equations that we're about to do. Now, if you take a look at the X and the Y that was reported, so this is the actual Y. This is the one that we predicted mathematically. We take the difference of each one of those. So we're taking 2 and 2.8, subtracting it, and we come up with a negative 0.8. And then here's the actual, here's the predicted, that difference is 0.6. Predicted, actual, 1, etc. And so we get all those values. Then we square them. And the reason we square them, this is a trick in math, is because it gets rid of the negative sign. It makes all numbers positive, right? And then we get the sum of all the errors or differences, and that gives us a value of 2.4. Right. So what does that mean? To most of you, like nothing yet, right? That means absolutely nothing yet. Let me get rid of these bad drawings. So what that's telling us is that we can figure out within a range how far off of that line we should be at the most. That's really what it means. So it says the distance between the line and the data points can also be minimized using these other techniques. So there's more than just the approach that we use, but all of them typically deal either with absolute values, squares, or the means of squares, basically, to get the results. But you notice none of the actual values really fit on the line. It doesn't mean the trend line is inaccurate, right? It just means that the observations don't necessarily fall on it, but the range that they are away from the line might still be completely valid. That's kind of the grand point here. All right. So what we're going to do is really quickly, and I want to show you back in the unit folder here, what some of these dependency files are. So the week 5 dependencies are here. So all the data that you need for the homework and the extra credit, and these examples we're about to do are in the zip file. I, of course, have downloaded and unzipped that here on my local machine. I put it in a separate folder. So these are all the files that you can see. And right now we're going to look at the files that are marked linear regression, and there's two of them. One is a Python notebook file. That's the file that you will use if you want to try to earn the extra credit, right? Which is to open up the Python programs and run them and get them to work, right? It's not really difficult to do because they're already pre-built, but I know some of you are still struggling with that stuff, so it's a chance to practice with it some more and play with it. But they also have what they call an HTML version, which if you double click that and bring it up in your browser, you will see this. And what they've done is they've summarized the key concepts here in this file and given you shots of what's in the notebook file so we can see the output, right? If I had a class that was twice as long as this, we would totally code all this stuff from scratch, right? But we don't have that kind of time, real frankly. So it's going to be on you to work with those code files to do that. They talk about what linear regression is, right? The most commonly used statistical method of predictive analysis uses linear relationships between dependent variables and independent variables to predict the future of the target. The prediction is based on the assumption that the relationship between the target and the predictors is dependent or causal. So if I put more gas in the car, I can drive farther, right? Cause and effect. How do you implement it? Well, they go into those basic formulas that we were talking about. So they have an example here. They found data about the price of a house that it's linearly dependent upon its size. So the bigger a house is, the more it costs. Makes sense, right? And it says, in fact, we found that a house's price is exactly 90 times its size. So knowing that, we could say that if a house is 1,500 square feet, for example, that it's probably going to cost 135,000, whatever. Okay, I don't know how true that is. They're just giving it as an example. They talk about the same equation that we were just looking at. I want you to notice this is the same linear equation. It's just looked at in let's call it algebraic notation here. We look at some of the same equations that we were looking at for figuring out the sum of the error of squares, so that we're looking for the difference to minimize the difference between the actual and the predicted over the whole range. That's what this equation does, right? Please don't freak out to the equations, right? Look scary, they really aren't, right? If we were to code this in Python, we would have to use these libraries. This is very close to the stuff that we've been doing as examples. And the extra credit for this unit is to open up the notebooks, get these to run, and then show it to me, basically, that you got it to work, right? So those are easy points because the code's already written. They go through the imports, they generate the data set. So they are basically setting up, and this is kind of weird, but they're setting up random values of a number. So they're doing a random number generator here to generate random X's and Y's. And here's an example, right? And based upon this random output, we're going to try to find some sort of a pattern in it. But when you have an X and a Y, and I want you to keep this in mind, when we have an X and a Y, we can take those data points, and that's 5.9. So if I, had like 5 points here, whatever, let's say this is 5.9, I'd come up, and this is 4.7, and I would find the point right here, and I would mark it on the graph. So each one of these can be put on a graph, and then you can see the pattern, right? Yeah, totally. If it's an X and a Y, very easy to plot and to visualize. All right. Then you start to calculate the mean and the covariance. So this is where we take basically the differences and figure out like what's the mean of all the X's, what's the mean of all the Y's, what's the actual versus the predicted, and we start to break that all down. And that helps us to get these two values for alpha and beta that give us a way to basically build the equation. So this is what all of this does, like that mathematical proof we saw on the slide, it's telling us what that data set, what its equation is to plot on the chart. Now, I want you to be mindful of this. This is a randomly generated set of data. So every time you run this, it's going to be different numbers, right? But this algorithm can still, based on using those formulas, can extract, we know that this, so this is written in a different format. This is the constant, this is the C, that's the point at which it intersects Y, and this is our slope. So it's kind of a flat line, right? A 1 would be like a 45, and the lower the number, the flatter it's going. But it's going up, but it's kind of flat, right? And so anytime I pump in an X, I can multiply it by this number, add that value to it, and it'll tell me the Y. So we can start to make predictions. So what we can do is we can feed in a bunch of numbers, right? And then we can predict the output based on that original formula. And this is where it gets interesting, right? So we took these random numbers, they got plotted, they created a data set, and then we used some other numbers, plugged them in there, and it created this based on that formula. So notice some stuff gets really close to the line, some stuff does not. But it is very clear, regardless of the line being there, that the data has a shape and a formation and an angle, no doubt, right? It's not like you have like dots up here and dots over here, right? It's all kind of in this general area right here in the middle, right? So that's linear regression, folks, and this is a real common thing. The other thing that we'll start doing as we kind of move forward is you'll notice like there'll be like a kind of like what we call like a range of like deviation here that's kind of standard, and like the amount that it varies, and I'm not doing a good job of drawing that. It's supposed to be a bell curve, it's not even close, but the normal distribution of a bell curve drawn along this line, if you can envision that, would encompass 95% of the data points or more. And we would know with a high degree of accuracy, plus or minus, it's going to be in a range. And you can kind of see it here. I mean, here on this side, I think it's a little clearer. It looks like everything fits there. This one kind of bumps out a little bit farther, but they're all in that general space, right? That's our linear regression. All right, we are at the 1 hour mark, so we are going to take a 5-minute break. It's 8:50. Let's come back at 8:56. All right, we're going to move on to the next topic now, which is talking about logistic regression. And notice this is different than linear regression. It's related, but not exactly the same. This is an important approach as well. And let's find out why. All right. So one of the reasons this was developed, right, is when we're working with a certain kind of data and we're doing regular regression, we can work with all types of data, but sometimes the data gets pretty complex, right? And sometimes we have a lot of different data points, and that complicates how we do a linear regression when you have a lot of data points, right? And well, logistic regression is basically taking some of that and sort of like, remember when we did like feature reduction, that kind of thing, or of some of our models. What we're looking at here is boiling it down to binary output to really determine like kind of a positive, a negative, a pass, a fail, a good or bad type of thing. And the way that it works, this is also based on statistics, by the way. And it says the dependent variable here, rather than being a regular number, is binary, meaning the output is basically between the range of 0 and 1, right? The same way that we would do percentages. We use it, it says here, to describe the data and the relationship between one dependent variable and one or more independent variables. And it says it can be nominal, ordinal, or interval type. So like all three different types of data. And if you guys don't remember what those are, those you should have learned in your data analytics class. But they're different categories of numerical information. We sometimes refer to this approach as what we call the sigmoid function. And it is something that's been basically developed a while ago. And as I mentioned, the basic output of whatever function you do boils down to being an output between 0 and 1. And whenever you have an output, the output is, it's not like, well, it's not like a precise science like a baseball batting average. It's pass fail. Did they Does that horseshoe count, or does that horseshoe not count? It's either there or it's not. It's not, and regardless of the outcome of it. And so this is kind of weird to explain. When we plot it on a graph, it kind of looks like this. So basically, it forms this like S-shaped curve that goes from 0 to 1, and this doesn't really show it, but it never really touches 0, and it never really touches 1. It gets infinitesimally close to both, but never really reaches either one, right? And why this was developed, as you can see here, to describe the properties of population growth in ecology, right? So in other words, they're looking at like a certain set of data, and at what point does, for example, a natural environment reach its capacity to support life, right? Like any natural environment can only feed so many individuals or water so many individuals, and you can have this growth up until you get up to a certain point and it can't support it anymore. So that's why it caps up. So there's like a limit, and that's kind of the point of it. What's kind of interesting about this, the general form of this equation uses the value of E, which is what they call the base of natural logarithm. So I just want to do a really quick little sideline here. Let me just bring up my browser. What is E in math? There you go, listening to us, right? And per Google's AI search results here, E is what we call, how do you like this, you guys? You guys see the message on my screen? You guys better not click on that. I'm kidding. All right. Right. We call it Euler's number. That's the guy who developed it, but it's approximately 2 point. Okay, I was wrong. I said 2.78 before, right? It's 2.718, right? You can kind of use that as sort of your calculations. But this is what they call the natural logarithmic function, and it forms one of the numerical constants of the universe, like pi or the speed of light, that kind of thing, right? Those are numerical constants. And they talk a little bit about where it comes from and all that. But whenever you deal with logarithmic equations, usually ones with curved lines, by the way, sometimes the E number is used as a basis for doing some of those calculations. So I just wanted to do a little sideline just to kind of point that out, right? If you guys never learned about that concept. When you get into higher levels of math and you start to do equations like the interest on a mortgage, that's a logarithmic equation that totally favors the bank, by the way, right? So when you get into a loan, most of your payment is interest, right? And then when you get to the end, it's mostly principal. So that's why it takes 30 years to pay it off, right? If it was flipped the other way around, they wouldn't make any money, right? That's why one of the reasons why you never want to get into a new mortgage if you can help it, unless your rate's that much lower, it saves you the money and the difference, right? Those are all different topics. Anyhow, what's kind of interesting about this is when it works best. So what are the advantages of doing this approach? It says it performs better when the data is linearly separable. So in other words, we can take all the data and split it into separate linear equations. So there are probably a lot of data points. When it doesn't require too many computational resources, because you can totally break it from running and still get good results. It doesn't require tuning because it's a pass fail. It's an either or. It says it's easy to implement and train, and it gives a measure of how relevant a predictor or the coefficient is and its direction, positive or negative. So it can very quickly give you results and be fairly accurate. And it's got a bunch of ways that we can use it too, right? So here's some scenarios in which this type of regression is used, right? Because if and some insurance companies are getting flack for this now, right? Where they automatically reject people, for example, like based on the zip code where you live, and it doesn't matter, it's too bad you're in that zip code. That's your car insurance rate, that kind of thing, right? But look at some of the uses. Banks can predict whether a customer would default on loans or not, or to predict the weather conditions of a certain place. This is pretty interesting. And this is kind of like we're having rain right now. It's about the storm's about to hit, if you guys aren't aware. And when you look at forecasts for rain, they always give you a percentage, and the percentage really means, not the percentage that it's going to rain or not, but how many people in the viewing area will actually get rain. So when this says 100% rain, everybody's going to get rain today. When it says 50%, well, half of you are going to get rain, right? Doesn't mean it's 50-50 that's going to happen, but half, it's kind of an example of it. Here's, the other ones you can read yourself, but otherwise, you basically use it really to classify objects based on little details, right? When we consider the fact that it's binary, right? The output is like true or false, or within the range of true or false. That means the dependent variable has to be that. So we have to have, a yes or a no. The light's either red or green. It can't be yellow. I mean, yeah, I guess it can be yellow, but it's red or green. You're either going or you're stopping, right? The other thing that you think about when you do this is when you're analyzing data using this approach, you don't want to evaluate data that really doesn't have an impact. Like before, when I was talking about the car and what tires it has on it, that's not really as big of an impact as like your MPG and how much fuel is in the tank as to how far you get, right? It has a little bit of an effect, but not a very huge one. The independent variables should be independent. They should have, they really shouldn't cross pollute each other, right? So in other words, if I change one, it's not changing the other. And they're linearly related to the log odds. So in other words, the potential of it. And the thing about this, though, is it requires very, very, very large sample sizes in order to work, right? All right, so here's where we start to go back to those dependency files again. So I'm going to take us back, and this time we're going to look at the logistic regression one. You notice there's a notebook file with that as well. And I'm going to zoom in, right? And they do a reintroduction of all the material here. So this is kind of like auxiliary text material, if you will, where they kind of boil down the concepts onto one page, right? So building machine learning models where the dependent variable is binary, multinomial, or ordinal in value, so one state or the other. It describes data and the relationships between one dependent variable and one or more independent variables, and then it can deal with any kind of independent variable, basically. All right, so what does this basically do for us is it gives us basically a really clear and finite way of making a decision, basically. We still follow the same kind of basic form of the equation. They're using different variable names here, but you notice there's a coefficient, and there's an x, and there's a constant, and there's a intercept, even though they're calling it z, right? But that is going to be basically either the positive or the negative result. You can add multiple variables to these, and then you can also plot it as we just saw in the PowerPoint. No reason really to repeat all of that. But if you want to see the mathematical proof in the equations that build this. Here it is, right? Not so scary. All right. We have this thing that we call the decision boundary. And when you work on a scale that goes from 0 to 1, the dividing point's right in the middle, right? So if it's greater than or equal to 0.5, it's a positive. If it's less than 0.5, it's a negative. It's just really as simple as that. So whatever output you get from your data, if it's up here, it's like horseshoes and hand grenades, folks. Up here, it's a win. Down here, sorry, next time, or whatever, right? It very clearly will fall in that range. We can use it to make predictions, right? As we have been talking about, there's some assumptions here. We talked about these in the slideshow too, so I don't think that we need to cover it. They talk about the different types, whether it's binary, which is the one that we're basically looking at here. There's the multinomial, so if you have many expressions or pieces of data, or the ordinal, where it has basically ordinal means information's categorized. Like, for example, gender, or something like that, right? That would be an ordinal value. There's examples here of running through data sets, right? They set up a number of samples, features, classes, etc. They visualize the data. Notice this is what the data plots, and it's either positive or negative. There's no in between ones on this one, but it's very clear where the data points sit. Now, this one feels a little anomalous, right? Because all the other red ones are over here. But notice how they plot that kind of in line with the sigmoid function. So like if you remember the shape of that, where it kind of goes like this and then flattens out, ran out of mouse space, whatever. Not very pretty art. But these points are being conglomerated here into the positive and negative, and it's because of that S-shaped thing that they fall where they do. This is definitely an outlier, though. Even though it's on the positive end, it is an outlier. Right. You take the data and you split it apart and you train it. So here's kind of an interesting aspect of this. When you work with data in this capacity, how do you know which data is going to have an effect and not? And that really comes through testing. You gotta dig into the data, you gotta dig into the models, you gotta figure out the equations and then test it. They have notice pre-built functions for doing this stuff. And they show here the coefficient, right, which is the angle of the slope, right? And the intercept, which is where it crosses the y-axis, that relate to that equation once again. And you do get your values here. You can build confusion matrices with these things, because we're working with binary information. And those are typically in the form of multi-dimensional arrays, right? And this is kind of the example for this one. Now, this is very much an overview of this tech, right? And we have one other tech that we need to dig into, which is the nearest neighbor approach. And let's jump back over to the PowerPoint here and kind of press forward with that. All right. So the KNN, right, and this is one that you see in machine learning a lot, is called the K. We use the K number, and then we look at the nearest neighbors of that K number, right? What's kind of cool about this, right, is notice what it says. We can design models for applications with sufficient domain knowledge that require high accuracy without a human readable model, right? So in other words, we don't necessarily have to know where this is going, right? We can predict on, I'm going to go back to that first example that we had tonight, where the guy either liked or disliked his classes, and it wasn't really anything that was necessarily measurable. You know what I mean? He either liked it or not. It was based on quality rather than necessarily numeric components. Um, the majority output, oops, I didn't mean to click there, is considered for classification, and we'll get some examples of that. And we did that with the red and the green, if you remember before, and why we choose an odd number. And then we also do look at the mean and the median while we're doing this for regression purposes, basically. Right? Notice that this particular algorithm or model approach is used as sometimes a basis for higher level, more complicated models. So often when we look at the SVM and the ANN that they're talking about here, we start with KNN first, and then we use that as the basis to build those others. We will talk about SVM here tonight. They call it here probably one of the simplest supervised machine learning algorithms. It's mostly used for classification, right? That's an orange, that's a banana, right? That type of thing. Think of it as like they're calling it here memory or instance-based learning. Like, how do I know that that's a banana and that's an orange? Right. Well, I remember what an orange looks like. Think of it like that, right? It's round and it's orange, And what does a banana look like? Well, it's kind of like long and curved, and it's a different color, right? So my memory tells me that's a banana, and that's an orange, right? They also refer to this, by the way, as lazy learning, which is kind of interesting. And why do they call it that? Because the learner doesn't do any training with training data. It just stores the data and during the training time and doesn't perform any calculation. So it's just storing the data. This is kind of interesting, right? And so what it says, the concept is to replace the model by memorizing the training data and then use the data to make predictions. Right. So let's move on to the next slide so you can see what I'm talking about here. Right. So this time we have little pluses, right? We have green ones and red ones, and you can see the red ones are all together and the green ones are all together. They're in their little areas on their own. And then all of a sudden we throw in this new one, right? The new data point. All right. So it says KNN will use a majority voting mechanism, and it trains the data to basically create, and you're going to see this on the upcoming slide, right? Well, this is our new data point, right? And then if I'm looking for nearest neighbors, I want to have at least an odd number. So you probably want to start with about 3. So I could draw a circle that maybe, this isn't a great circle, right? Maybe grab those. It's not even a circle. Look close, right? And now you could argue, all right, I could clear that, right? That maybe these 2 red ones here are really closer, and I'm missing with the circle, but you guys get the point, right? That maybe those red ones are closer than the green ones are, and really I should be grouping 2 of those and 1 of the green. It really sort of depends. So where you start when you do this kind of thing is which one's closest, right? So it's kind of a common sense thing. Like you plot it, and then you ask that very simple question. All right, so you move on to the next slide. So we start here, and this is a little bit better example. So this is the new unknown data. So I create a K of 3. I incorporate the 3 closest. I'm using an odd number because if I use an even number, there could be a tie. Right. So we use an odd number. It doesn't matter what that number is. We have examples of 3 or 7. Right. And what we want to do is predict where does this fall, right? And, how do you really determine that? All right. So because the data is plotted and it's clustered and we can kind of see it, it really helps us to visualize this conceptually. So we group it based on feature similarity. We're not really looking at what the data is. We can't tell if it's an orange or banana, right? So we just keep widening that circle to its nearest neighbors, incorporating data from both groups until we can compare enough to go, okay, it's really much more like this one, or there's much more of these that are close to it than these that are close to it. That's a better way to say it, right? Right. And the concept of like changing that K number and widening it or making it smaller to reach the right value of K to make the prediction, they call that parameter tuning. So when you hear people talking about that, that's what they're doing, is they're changing that K number to see how many nearest neighbors we're pulling in to look at to make the determination, right? So if the value of K is too low, there's too much bias because it, you know, 2 to 1 is not, really a great vote. You know what I mean? Right. All right. If it's too big, it can create a processing issue because we have to crunch the numbers for all the stuff that it's included, right? So you don't want to make it too big. You don't want to use like a 10-digit number. Probably doesn't make sense. All right. As K approaches 1, meaning when it gets too low, it becomes less stable, so it doesn't really predict as accurately. And once again, that odd number thing. And the whole reason for the odd number is to not have to have a tiebreaker, right? If the data points are really close, right? Some things to think about. It says here, as the value of K increases, prediction becomes more stable due to the majority of the voters. It becomes you're adding more data, so it's better. But as you add more K, right, more K values, it's a lot more computing resources, a lot more. And if your models, like if you were doing this, like working a live model, and you notice, oh, I made my K too big. Oh my God, it's taking an hour to process this, that kind of thing. Because that's what happens, is when the K number is too big. All right. Let's take a look at some examples here. I do want to state up front, clearly this person is not an American that put this slideshow together, right? Because that does not look like a football to me. That looks like a soccer ball to me. But we'll go with it, right? We'll pretend like we're in Europe for a second, right? All right, so we'll call this a football. Right? So one example would be to label an object. Another would be to look at some data, right? So noise-free data, so meaning data that's clean and doesn't have any weird stuff in it. In this case, we're looking at people and we're looking for them to be ranked, and this would be data with noise because it's got the wrong kind of data in the data field. That would be noisy data, by the way, or working with really small data sets. All right, let's kind of dig in and figure out how this stuff works now. It says, consider a data set having 2 variables, total marks out of 1,000 and attendance percentage, right? And then each one is classified as a pass or fail. This is kind of interesting. And you know what? I think it's kind of, I don't know if these numbers are accurate, but I see it, right? When I look at a student who shows up every week, they tend to succeed at a much higher rate than those that don't. Okay, right. Well, you heard what you're supposed to do. You did the stuff, you went to class, et cetera. So that's really kind of what we're looking at here. So if you just examine your data, right? Really high attendance, good score. Really low attendance, bad score. And notice, bad result, pass or fail. So ultimately we're determining, is this person passing or failing on this scale? We don't, really know. Right. So looking at that data, if I give you this new data that's not on the table, this is a really good example. So I have a attendance amount, fairly high, marks, not all that high. What should we do with this person? Okay, let's just be really practical about this. I might go back here and let's look at this and go, all right, well, what was that? 68 and 570. Well, this is 70 and 690. This is 65 and 630. All right, you know what? Here's a 40 and a 560, and they passed. Well, my attendance is higher and the number's about the same. I'm going to call it a pass. This is just a common sense approach. But I want you to think about like what I just did verbally. I kind of did the nearest neighbor thing. I'm like, I don't know what this should be. I don't see a formula or anything. So let me just look at other ones that are kind of nearby. Well, if this one's got that low of attendance and that score, if 560 is a pass, then I'm gonna guess 570 is gonna be a pass with 68% attendance. Is that a fair guess? I think that's a pretty fair guess. Okay. You guys aren't so sure, right? Well, we can, because we're plotting this stuff on a two-dimensional graph with an X and a Y, we can use the distance formula to basically calculate the distance from our new point to all the neighboring points. Okay, so now we're applying math, and this is where the number crunching comes in. So any point that we plot on a graph has an X and a Y coordinate. Right? You guys remember this from like geometry class where you totally hated it? Right? Or trig class, maybe is, I don't know where you guys would learn this these days, algebra even. But any XY point or any two XY points on a graph, I can figure out the distance between them. And really what we're doing when we say Euclidean math, by the way, what we mean is like this forms a right triangle, right? And this is, a right angle, right? And we have an A side, like this is A and B and C, and A squared plus B squared equals C squared, right? And then if you want to find the length of C, this is basically the formula for it. You take the x's, subtract them from each other, square them, subtract them from each other, square them, add them together, take the square root, and that's the distance, right? This is like the basis of all like modern geometry, basically. So when we say the Euclidean formula, we mean the distance formula, and we mean a squared plus b squared equals c squared, or the quadratic formula, or whatever you want to call it, right? This is pretty common. But if we're analyzing, think about this, all of our data points that we have, and we're comparing it to our new data point, and then using that new data point to determine the distance to all the nearest neighbors, right? So we can run that formula. We can take our new data point, and notice the 570 here, right? And we're doing distances to all the nearest neighbors. And we know like this one's a fail and this one's a pass. We seem to be closer to the passes, although this one was a pass too. So I don't know like what the demarcation line is exactly for pass. We're not really told, right? But apparently it's like 50% is pass. Okay. All right. But that's how we do it. So like if we think about this, if we're creating circles that are wider, well, then we would take the distance to all of these points, right? We can measure all of those points and combine those calculations and use it in powerful ways to make a lot of different types of analysis here. So now they're saying, let's set the K number to 3. All right. And we're going to put in these, this is our new data here. And we find the 3 nearest neighbors, right? Looking at the chart or looking at the table, however you do it, right? All 3 of the nearest neighbors, and this is kind of the technique I used, right? Just by looking at the table, are within range. All of them are pass, so we should pass with that. Okay. And there's all the majority neighbors, all in this case, all of them. There wasn't one that was fail. All of them passed. And I don't know if those were the best data points to use, but they seem, the one that I thought was closest was this one because of the 570, and their attendance was bad. If they passed, ours had to pass, right? Okay. Yeah. All right. One advantage of this, right, and even though we talk about processing speed and stuff, KNN works pretty darn fast, and this algorithm has been around for a long time, has been used really heavily in the machine learning world like forever, right? And we're talking back decades and decades. It's a very simple algorithm to work with when you start out. Um, you can use it for a lot of different situations. It usually yields very good results. And you don't, the bottom bullet, you don't have to make any assumptions about the information that you're putting in there. You don't have to keep tuning it a lot. It's usually minimal tuning. And it becomes a really critical tool in this field of work, right? This particular algorithm is a very, very important one for machine learning, one of the more critical ones. Right. There are some disadvantages, right? As with all models and algorithms and stuff. If you want it to be accurate, you have to give it accurate data, right? So it's like the better your data, the more accurate your output will be. So if I'm like, for example, if I throw onto that chart like students that never showed up to class, or if I had, I don't know, I fudged the numbers or something like that's not going to give me good results. So I have to use real numbers, basically. Um, it says that with a large amount of data, it can be kind of slow to predict. Um, so it does scale well to the data itself. Um, but one thing to think about here is because all the data that you're comparing to is going to need to be stored in memory as you're processing it. If you use a lot of data points, it can really consume a lot of memory in the model training. Right. So they call this kind of a computationally expensive algorithm. So like if you are paying to run this algorithm on some cloud service like AWS or Google or Microsoft, right, where you're paying by your computing hours, this can be a very expensive algorithm to operate. So that's one of the things. And folks, a lot of people do their models that way. They do it basically on cloud platforms. They get the built pieces and then they move to the cloud platforms because they have the computing power to process it much more quickly, but that costs, right? Rather than owning the equipment to do it. Next, we're going to look at support vector machine. And this is another aspect of supervised learning that's important. And this is kind of an interesting approach because, it is related to KNN. And I think we mentioned earlier that KNN becomes like the foundational piece for a lot of other algorithms, including this one, right? Okay, so normally the way that we are able to do this is, remember this concept of like converting stuff to a higher dimensional space, so to create like more data points or dimensions within your data or features, if you will. And what they're kind of saying here is that the way that it does its classification is it improves without like pushing the data too far. So in other words, if we're looking at this data space, and I just want you to look how messy this is, and I can see that there's stars and dots. And for the most part, the dots are on the bottom and the stars are on the top, but I really can't draw a straight line through it. Right. And what we do is we do this thing where we call mapping it to a higher level or dimensional space so that we can actually create a margin. And what we're usually trying to do is maximize the separation of the data so that there's a clear delineation between what's a star and what's a circle, right? And we do that by increasing that space, because here that would be very difficult to do. But we can use that increased space to then convert back down and find the actual pathway of where the delineation is, so that when we get new data, we are spot on. right, with the data. So this is kind of a weird technique. So what is kind of weird about this also is that it is um, really well suited to working with ridiculously large data sets, which is why this technique is used. So when you have lots and lots of things to map, this becomes particularly useful. So just to kind of go through that again, we map the data to a high dimensional feature space to categorize things, right? And that is because we can't otherwise draw a line in between. That's what they mean by linearly separable, right? I can't draw a line in between it, right? We find a separator between the categories by converting it to an upper dimensional space. And then we transform that data to what we call a hyperplane. So that's a plane that's not flat, it's like curved and stuff. And then we overlay that back onto the original data set so that we can make accurate predictions with new data, right? So once again, what that looks like. Here's the original data set. We got black circles, white circles, right? Or filled circles, empty circles, whatever. And we can put the separator in, but when we map it to the high dimensional space, we are basically mathematically forcing a division in between to make it very, very clear what's what, where it sits, and there's no overlap. It's clear, right? When we do that adjustment, or what they're calling a transformation here, this is a kernel function. I'm not sure why they call it that, but that's what they call it. Right? Some of the reasons we use this technology, right? So when we use facial recognition, uses this technology. When we are analyzing like the structure of DNA and medical things and stuff, so bioinformatics, and when we're classifying images, right? And all right, well, we're talking apples, oranges, and bananas. Let's go back to footballs and basketballs, and I'm saying that with like tongue in cheek as an offended American or whatever, right? And I did feel compelled to go in there and drop little footballs in, and I'm like, nah, I'm not going to do that, right? All right. So Sam and John run a sports shop. He put his son at the counter, and his dad asked, "Is that a football or a basketball? A soccer ball or football?" And and it depends. Which one is he pointing at? Right. So if he builds a model, right, can we predict what an object is, right? And we did this. If you guys remember, we did play with one machine learning tool, and we demonstrated it here during class, during the AI class, where I think I was holding up like a roll of tape and a battery tester or something goofy like that. And my battery tester is still sitting here, by the way. And we trained it, right? And we trained it by letting it look at one of the things and moving it around and then showing it a different thing. And then we could bring in a different object and put it up and go, what is this? And it would tell you, right? And that's kind of the point. So the way that it works, of course, right? So once again, starting with data that is already labeled. We know what a football is and we know what a basketball is. All right. And Brandon, I see you have your hand up, sir.
I was going to ask you about when it comes to training data. So sometimes when different people are training data, like they're using not only they're using data, they're using like pictures, they're using all these different things that kind of feed the machines with.
Mm-hmm.
So it'll know like so I'll give an example. Like say I take a picture of my Spanish homework and I need to learn a word or a sentence of what it means. Because someone's actually put that data in there a while ago, they'll be able to interpret what I'm saying based upon the large data sets. And that's pictures and that's words, correct?
Correct. And
Okay.
the models still need to be trained, though. I mean, Brandon, I
Okay.
mean, this is, you know, an aspect of it. I mean, the natural language processing aspect of it is a little bit different, right? And especially when you start to deal with foreign languages, because, but it's true, right? Like if you have a word in, let's say, pick a language, and then you compare it to the English word. I mean, that's not going to change, right? But that word is that word. Well, for the most part. And then you get weird languages, and Greek is one of those weird languages, and which I know, right? Where sometimes you put the joke here, emphasis on the wrong syllable, and it means a completely different thing in that language sometimes. Like on the one hand, you're complimenting somebody, and then the other hand, you're insulting their whole family, you know? So you got to be careful with how some of that works. Anyhow, going back to this, we do start with labeled data. So we know what a soccer ball and a basketball look like. So then we pick up a new ball and a new ball, right? And so how are you really training your model? By using things that are already labeled that you know is a soccer ball and you know is a basketball. Then you grab a new ball and you throw it at the model and it will predict what it is. And it should be, you know, in principle, accurate. That's what it is. Now, like I said, in the previous class, we experimented with that one machine learning engine. We actually experimented with a couple. But I thought that one worked pretty darn well. And if wasn't that a Google product, you guys? It was, I think, right? I don't even remember which product it was at this point. All right. So to look at it from a data point standpoint, right, we have stuff that's already labeled, clearly grouped, clearly largely separated. There's a definite boundary in between with a large margin. We throw new data at it. So it's kind of close, but one's clearly a soccer ball and one's clearly a basketball. Right. Right. So basically, I mean, it uses sort of, you know, a binary approach here. Once again, it's going to sort it into two categories. Um, you know, we can plot the stuff, right? We know certain things. I mean, we all can look at it, like especially if you have vision, and know really quickly which is which. What are the differences? Well, color, shapes of the patterns, right? If you could touch it, they would feel different too, right? Like basketballs have like those little like super tiny dimples on them and have a different kind of rubber. And then soccer balls have those like hexagonal, or what is it? Is it hexagonal, or yeah, it's five-sided shapes, right? And they're all stitched together. So you could probably, like, if you were blind, you could touch it and feel it and figure out what it is. Or maybe you know that a basketball weighs this much and a soccer ball weighs this much, right? I think a basketball is much heavier, if I'm not mistaken. I'm not really sure though, right? But you can plot it, right? All right. Then we try to set up the data points to create a clear separation, right? And notice all the lines they've drawn here is to create hyperplanes, even though these are just lines, but we can imagine a plane going through here in 3 dimensions. And it could go through at an angle. I mean, it's possible, given this graphic, that it goes straight up and down, right? Right. So 2 possible data points, and then you find hyperplanes that work. There's many that could work, but really what you want is the hyperplane that allows for the maximum amount of space on either side of the data, right? So that's the best hyperplane or the best fit to make our decision point. And that way, it'll be easier to make the prediction, right? Now, the difference, right, on the one side, you know, the shortest distance to a basketball, the shortest distance to a football, so to speak, is determined by that D minus or D plus. And basically the values that give us the maximum D on both sides are the ones that dictate the optimal hyperplane. That's kind of a weird thing to say. All right. So what happens if the hyperplane is not optimal? All right. So when I'm putting stuff on a chart and I'm throwing all the stuff in one corner and the other stuff in the other corner, well, you know what? That's really easy, right? Like the top right graphic, all the basketballs are up there, all the footballs are down there. But what happens if you have graphics like this, where, okay, well, these are on the line and there's a blue one here. That's not good. Or what if they're not in groupings like this? There's a grouping in the middle and all the rest of them are sitting around pointing and laughing. I mean, um, they're in a circle around there. I'm teasing here, but the concept is the data doesn't group in a way that you're comfortable with, where it's really easy to see. So what happens in those situations? Well, there are ways that we can work with that, and this is where the kernel thing comes in, where we basically transform our data into a higher dimensional space to give us the separation so we can draw the hyperplane and transform it. So, all right, so this is what this is explaining. So basically the kernel function is used to take data as an input, transform it into the required form of processing data. It takes the training set of data, so that nonlinear decision surface is transformed into a linear equation in more dimension spaces. So we're just basically, we're leveraging math here to make it work. So ultimately the kernel is really a dot product. And if you guys remember what a dot product is, it's multiplying a matrix or a whole table against a whole table. It could be small, it could be large, but that's called a dot product. And that's how we raise the dimensional space. So for example, if I have a bunch of points on a single line, we can call this a one-dimensional line, right? These are my data points. Here's the what it would be the optimal hyperplane right in the middle, right? But then we had these two over here, so that doesn't really work. So we use the kernel to up the dimensional space mathematically, and then we plot it in 2 dimensions. We're adding a dimension to it. We're adding a y. And then as we add the y, which allows the points to lift off the line, now I see a division where I couldn't find one before. And this is a really nice little example, I think. And this is going from 1 dimension to 2. But you can also, right, and we've learned about this, that all the data points you have really determine a dimension, right? So however many data points you add, you're just adding another one by upping the dimensional space. So you can go from 2D to 3D, 3D to 4D, or however many you can determine, you know, with the kernel transformation, right? So when we take a 2-dimensional graphic where the stuff's grouped in the middle, and we transform that to a 3-dimensional space, so now it has height as well, then once again, you'll see that the data separates because it's separating in a way that you can't see in 2 dimensions. And this is a crude representation of 3-dimensional space in a 2-dimensional world, right? You wouldn't see this, but this is what the SVM gives us, is this transformation from 1 dimension to a higher, so we can see the division, and then our classifications work much better. So that's the algorithmic approach behind it. All right. Where this works well, okay, obviously in high dimensional spaces when there's lots of data points, right? It's also really good when the number of dimensions exceeds the number of samples. So you got, like, you might only have 10 data points, but each one of those data points has 20 variables, you know, in it, something like that. Because of the way that it works, right? It uses subsets of stuff. It's a pretty efficient algorithm, which is one of the reasons why it's very popular. And you can use different aspects of it based on like what you're trying to decide upon, right? So like, how are you looking at the data? You can leverage different aspects of the data with the kernel function to focus in on the parts that you want, right? One disadvantage is what we call overfitting, right? It says if the number of features is much greater than the number of samples, avoid overfitting, and choosing kernel functions is crucial. So in other words, we're trying not to force things to be categorized. Kathleen, you have your hand up.
Yep, just a really quick question. Does it typically just increment 1 dimension up one dimension, like it went from one dimension to two dimension, then two dimension, three dimension, or can you specify what dimension you'd like to have it at?
You can actually, but usually when you're dealing with however many dimensions that you have, it's a it's a process of selection. So like it's like selecting the right ones to upscale because they're not clear the way that they're currently plotting. And so sometimes you have to take the data, run it the way it is, and then go, okay, we're not seeing anything clear here. Let's add a dimension to this aspect, and then we'll see what happens there, right? And that can be a trial and error process, right? The overfitting part is to try not to force it to go a certain way just because you want it to. That's what really they mean. Um, okay, so they have this last statement here. It says it's expensive five-fold cross validation. And it says SVMs do not directly provide probability estimates. Okay, so it doesn't tell you exactly how certain it is that it's right on a percentage. This is kind of interesting. They're calculated using a five-fold cross validation. So you have to do extra math to figure that out. All right. I do have, and I'm going to do this super fast because I know we're out of time here, an SVM page here as well. And this one's very similar. And it shows you the techniques that you can use in Python to run this. And this is part of the extra credit as well. And there's just two lines of text here I'm going to read. Basically, it's robust. It's a regression technique that maximizes the predictive accuracy of a model without overfitting the training data. It's particularly suited to analyzing data with very large numbers, for example, thousands of predictor fields, and is a very, very popular algorithm built on top of KNN. And they go through the process here of loading all the libraries, loading in data sets. In this case, they're analyzing pixels on a screen, turning it into an array, loading more, determining the length, et cetera, and then evaluating the accuracy. And if you run all of these, this will tell you how accurate the model is at the end. It'll give you a score. And the score will be in the form of a percentage, and it will tell you what the accuracy is. And if I ran it and I got a pretty high number on it, this is a very good training data. All right, folks, I'm going to cap the lecture here. I think we made it through all the slides. I better go back and make sure. I think that's it. Yep, that's it. All right, so this video ends here, folks.